Here are two transformations of a house. On the left, we rotated 45 degrees. On the right, we shifted 3 units to the right. Both move the house rigidly. Both look reasonable, but only one is linear. The test that separates them is shockingly simple, and it comes down to just 2 rules. First, a transformation is just a function. It takes a vector v from one space and returns a vector t of v in another. We write this as t from v to w. Think of it as a machine. You feed in a vector and you get a vector out. Rotation is one such machine. Shifting is another. And so is projection onto a line. The real question is, which of these machines respects the structure of vectors, namely addition and scalar multiplication? Here are the 2 rules that define linearity. Rule 1 is additivity. T of the quantity v plus w equals T of v plus T of w. In words, transforming a sum is the same as summing the transforms. Rule 2 is homogeneity. T of c times y equals c times T of v. Scaling first and then transforming gives the same result as transforming first and then scaling. We can fold both rules into a single equation. T of cv plus dw equals c times T of v plus d times T of w. If this one equation holds for every choice of vectors v and w and every choice of scalars c and d, then T is linear. That is the entire definition. An immediate consequence, every linear transformation sends the 0 vector to the 0 vector. Watch this. T of 0 equals T of 3 times 0. By the homogeneity rule, this equals 3 times T of 0. But the only vector equal to 3 times itself is the 0 vector. So T of 0 must be 0. This gives you the fastest diagnostic in all of linear algebra. If a transformation moves the origin, it cannot be linear. Let's stress test these rules with 5 candidates. First up, projection onto a line L. Take a vector v, drop a perpendicular down to L, and that shadow is the projection. Now double v. The projection doubles right along with it. Flip v to negative v, and the projection flips too. Add 2 vectors, project the sum, and you get the same answer as projecting each one separately and adding the results. Projection respects both rules. It's linear, and the origin stays put at the origin, so it also passes our diagnostic. Now for the second candidate, a shift by a fixed vector v0. The transformation t sends v to v plus v0. Let's run our diagnostic. Plug in 0. T of 0 equals 0 plus v0, which is just v0, and that is not the 0 vector. Instant fail. But let's also look at additivity to see exactly how it breaks. On one hand, T of the sum v plus w equals v plus w plus v0. We add the shift once. On the other hand, T of v plus T of w equals v plus v0 plus w plus v0, which is v plus w plus 2 v0s. One extra v0 appears on the right. Shifts are not linear. This, by the way, is exactly why the familiar line y equals mx plus b is called affine, not linear. The plus b is a shift that breaks the rules. Third candidate, length. We define T of v to equal the norm of v. The origin maps to 0, so the diagnostic check passes. But now let's check scaling with a negative scalar. Suppose v has length 3, then negative 2 times v has length 6. Because length is always positive, so T of negative 2 v equals 6. But negative 2 times T of v equals negative 2 times 3, which is negative 6. 6 does not equal negative 6. Negative scalars expose the failure. Length is not linear. Fourth candidate, rotation by 45 degrees. Geometrically, rotation preserves the parallelogram rule. If you add v and w first, then rotate the sum, you get the same vector as rotating each one separately and adding the results. And doubling a vector before rotating gives the same answer as rotating first and then doubling. So rotation is linear. Fifth, matrix multiplication. T of v equals A times v. Here, Matrix algebra hands us linearity for free because A times the quantity CV plus DW equals C times AV plus D times AW, linear by construction. Notice the pattern. Projection, rotation, and the matrix multiplication, all linear. And here's the punchline. Every linear transformation between finite dimensional spaces is multiplication by some matrix. Linearity is defined coordinate-free, no numbers, no grids, just behavior. But once you pick a basis, that behavior compresses into a grid of numbers. Let me verify with one calculation. Take A equal to the diagonal matrix with entries 1 and -1. Let V equal the vector 1, 0, and let W equal the vector 0, 1. Choose C equals 2 and D equals 3. On the left side, T of 2V plus 3W. 2V plus 3W is the vector 2, 3. Apply A to get 2, -3. On the right side, 2T of V plus 3T of W. T of V is 1, 0, so 2T of V is 2, 0. T of W is 0, -1, so 3T of W is 0, -3. Adding these gives 2, -3. Both sides agree, match. Back to the house. Apply that same matrix, the diagonal matrix with entries 1 and -1, to every point of the house. The base stays put, but the roof flips downward. The chimney now points at the floor. One matrix acted on infinitely many vectors simultaneously, and because the map is linear, the whole shape transforms coherently. Quick summary. Projection is linear. Shift is not linear because the origin moves. Norm is not linear because negative scalars break it. Rotation is linear. Matrix multiplication is linear. 3 takeaways. 1. Linearity means T of CV plus DW equals C times T of V plus D times T of W. 2. T of 0 must equal 0, your fastest diagnostic. 3. Linear does not mean line-shaped or simple. It means the two rules hold. Linear is a behavioral property, not a visual one. When the rules hold, a matrix appears, and the whole machinery of linear algebra opens up. When they fail, you're outside the theory and you will need different tools.